Welcome. Good to see you again. Glad you tuned in to figure out how do I combine and simplify radical expressions. Great question. So let's jump into it. I want you to simplify each of these first. These aren't radical expressions. These are things you've seen before. Pause the video, simplify them, and pause when you're ready to share. All right, so hopefully you got 8x, 12y, 2w, and then this one we can't really do anything with, so we just leave it as the expression 5x plus 3y. Now, I really hope that was pretty easy and straightforward. I wasn't trying to trick you there. And if you are confused on anything, please, let me know. So how do we do this, though? We want to talk about why this works, right? This is literally saying there's 1 of this thing plus 7 of this thing, right? This is how, when you first learn addition, whatever grade that is, you have I have 1 apple, you have 7 apples. How many apples do we have together? We have 8, right? That's what this is, but instead of apples, we have x's. Here we have y's. Here we have w's. Here we have x's and y's. So I have 5 apples, you have 3 oranges. Together we have 5 apples and 3 oranges, but that's all we can say. The same is true when we're adding or subtracting radical expressions. And so that's why I wanted to show you that first so that we can understand, well, as long as the index, so these are both 4th roots, remember that is the index, and what is underneath the radicand, so in this case it's 10, as long as those are the same, then we are adding or subtracting the same thing. This whole expression right here, 4th root of 10, that's like my x, right? And how many of these things do I have? Well, I have 1 of them. How many of them do I have here? I have 7 of them. So what do I have? I have 8 of them. So this is 8, 4th root of 10. Here, I have 2 times 8 to the 1/5. Remember, 1/5 is actually the same as the 5th root of 8. We have seen that. And here I have 10 times 8 to the 1/5. So the radical part, even though it's written as a rational exponent, it is still considered a radical, is the same. The same index, 1/5, and same thing underneath the radical, 8. So for this, we are going to have 12 times 8 to the 1/5, because 2 plus 10 is 12. Now here the parentheses are really just to make sure that it doesn't look like we're writing 128. Okay, next one. Now these aren't the same. So am I done? Well, if this was x minus y, I would be done. But because we're dealing with radicals, I do want to see, can I break this down? Right? And so I think about, okay, well, 54, what are my perfect cubes again? So I've got 1, I've got 8, I've got 27, I've got 64. Okay, that's already too much. So if I go in my calculator, I can see, well, wait, what is 54 divided by 27? Huh, that's 2. Nice. All right, so I can think of this as the cube root of 27 times the cube root of 2 minus the cube root of 2. And the cube root of 27 is 3, so I've got 3 cube root of 2 minus cube root of 2. So this becomes, wait for it, 2 cube root of 2. Look at how we did that. Look at that. All right, nice work. Now you try. So I want you to do A and B, pause the video, and pause when you're ready to discuss. All right, so hopefully the first one was pretty straightforward, and we get 11 root y. 5 plus 6 is 11. Both of them had the same index and same value underneath the root, so we get 11 root y. Now the second one, maybe you had a little more trouble with this. This is going to be more work and involves some things we've discussed and some that you might have had to kind of think about a little bit more on your own. So how do I come up with this? Well, first thing I notice, or the answer is 9z cube root of 2z squared. How do I come up with that? Well, first thing I notice is that the index of the radicals are the same. They're both cube roots, but what is underneath the radical is not. So going back to our problem here, I'm going to try to break things down if I can. And maybe it works, maybe it doesn't. So first I looked at this, and the first thing I did was I separated the cube root of 2z to the fifth as the cube root of 2 times the cube root of z to the fifth, because we know from properties of radicals I can do that. The cube root of 2 I can't simplify at all. So I know that's just going to stay there, so I'm just going to temporarily ignore it. But I'm going to focus on the cube root of z to the fifth. Well, in order to break this down, I need z cubed, since this is a cube root, right? So if this is the cube root of z to the fifth, I can think of this, using properties of exponents, as the cube root of z cubed times z squared. Now again, properties of radicals, and here, similar to some other things, I'm showing more work than maybe is necessary, but hopefully it's helping you understand where I'm coming up with this stuff. So then I can separate them again, and I can say, okay, well, the cube root of z cubed is z, and then the cube root of z squared just stays the cube root of z squared. So the cube root of z to the fifth becomes z cube root of z squared. Now when I put it all back together, well, the 12 is still there, but now this z is multiplied on the outside, so that's how I get 12z. And then I have the cube root of 2z squared, because the cube root of 2, again, didn't go anywhere, it just still stays there. For z cube root of 54z squared, so here I can separate this just like I did here with the number and the variable. However, I know that the cube root of z squared isn't going to simplify. So really I'm just focusing on the cube root of 54. And we've already seen that one as well. We actually did that on the previous page too. So I broke that down into the cube root of 27 times the cube root of 2, so that's 3 cube root 2. So then back up here, this is the 3, and then this z is still the z, and then this was the cube root of 2, so that's that 2, and then I still have the z squared. So now the index of the root is the same, and what's underneath the root is also the same. So I can combine the values on the outside. 12z minus 3z is 9z, and I have the cube root of 2z squared. All right, so let's practice this breaking down roots a little bit more. So the first thing I want to point out is using one of our properties of radicals. Anytime I have multiplication, which I do here, or division, which I do here, remember I can think of each part individually. Under that root is what I mean. So what I'm showing you is my thought process. I would think of this as the cube root of 64 times the cube root of y to the sixth. Now I would say, okay, is 64 a perfect cube? Yes, it is. 4 cubed is 64. However, if it wasn't, then I would do what we've done before, and I would try to break it down into what is its largest perfect cube that's a factor. So in this case, this part just becomes 4. Now, the cube root of y to the sixth. So there's two ways I can think about this. One, I can think of this, remember from earlier, this is the same, if I just rewrite it as a rational exponent, as y to the 6 over 3, which is y squared. So I know this part here is going to be y squared. Now the other way to think about it is similar to what I did on the previous problem, and that is to take this and say, okay, well, I know that if I have the cube root of y cubed, that will just become y. So I can try to break 6 down into y cubes. So I can think of this as the cube root of y cubed times the cube root of y cubed, because y cubed times y cubed is y to the sixth. And I know each of these, this is y, and this is y times y gives me y squared. So again, going back to actually my answer here, it's going to be 4y squared. Questions on that? Okay. Similar thing with division. So here I have a fourth root, right? So I'm going to first think of this as the fourth root of x to the fourth, and we know that's going to be 1, or x, just 1x. And then I can think of this as the fourth root of y to the fourth times y to the fourth, because that would be y to the eighth. And so then this becomes x over y squared. All right. So again, just kind of sum it up. You're going to do some practice in a minute here, but my thought process of just separate each thing individually, simplify that as much as possible. If it's a number, you're looking for, in this case, perfect cubes. If it was a square root, perfect squares. If it was a fourth root, perfect fourth powers. Use your calculator to help you with all that stuff. And if it's a variable, you're looking for just how many of that exponent can I break out of whatever is there. So in this case, if I have y to the 8th, but it was a fourth root, well, I can get 2 powers of 4 out of it then. All right, I want you to try these. Pause the video, try these, take your time, unpause when you're ready to discuss. Okay, so let's see what we got. So for the first one, I got ab squared c 5th root of 4a cubed b to the 4th. Now, a couple things to check. So the exponents in here should never be larger than this number. If they are, then I can simplify more. But if you're confused, let's talk about what I did. So again, the first thing I did was I just split this all up, right? So I thought of it as the 5th root of 4 times the 5th root of a to the 8th, 5th root of b to the 14th, 5th root of c to the 5th. Now this one right here, the 5th root of c to the 5th, since these exponents match up, I know that just becomes c, no more root. The 5th root of 4, well, 4 is not a perfect 5th root, and none of its factors are either, so that's just going to stay 5th root of 4. So that's why I highlighted it. That'll just be part of my answer. That's why I highlighted the c, because this is part of my answer also. So then the 5th root of a to the 8th, I thought of that as the 5th root of a to the 5th times the 5th root of a third, because a to the 5th times a to the third is a to the 8th. The 5th root of a to the 5th is a. So this piece here that I underlined in blue became this in blue. So a 5th root of a to the third. So I know this is going to be part of my answer. Then the 5th root of b to the 14th, this became the 5th root of b to the 5th times the 5th root of b to the 5th times the 5th root of b to the 4th, because b to the 5th times b to the 5th times b to the 4th, 5 plus 5 plus 4 is 14. The 5th root of b to the 5th is b, the 5th root of b to the 5th again is b, and the 5th root of b to the 4th just stays the 5th root of b to the 4th. b times b is b squared. And I still have the 5th root of b to the 4th. So now it just became a matter of putting it all together. So what things are outside of the root? I have the a, the b squared, and the c, and what things are still in the root? Well, I still have my 5th root of 4, I have the 5th root of a to the third, and I have the 5th root of b to the 4th. So that's how I got a, b squared, c, 5th root of 4, a to the third, b to the 4th. This one I didn't really show any work because it's really basically the same thing as what we did here, just different numbers. And the numerator had the 10 in this case, or 2 times this number. So x to the 10th, I can think of that as x to the 5th times x to the 5th. So the 5th root of x to the 5th is x, and x times x is x squared. The 5th root of y to the 5th is y. Next one. So here, again, I think of each part individually. So the numbers, 14 over 2, that's 7. Okay, that's part of my answer. Just leave it. X over x to the 3/4. Okay, well, I know I need to subtract the fraction, or subtract the exponents, right? So 1, because this x is x to the first, minus 3/4. Well, I have to get a common denominator, so 1 in this case is 4 over 4 minus 3/4. 4 over 4 minus 3 over 4 is 1 over 4, so I get x to the 1/4. The y to the 1/3 has nothing to combine with. And then z to the -6th, well, since this is in the denominator with the negative exponent, I can bring it up to the numerator with a positive exponent. So that's how I get my answer of 7, x to the 1/4, y to the 1/3, z to the 6th. Okay, so it's important to understand how to combine radicals. We need to have the same index and value under the radical in order to be able to add or subtract them. And then when it comes to just simplifying, we just use our skills of breaking down radicals. Use your calculator to help you if you need to with some of the numerical values, but it really just takes practice.